telescopes at prime focus, and I have a 10-inch Mac that I can use at a focal ratio, or a focal length of about 11.5 meters.
Wow.
So this was a beautiful double rainbow that stopped traffic in New Hampshire on summer vacation a year or two ago. This is the mighty Niagara River, and the moon and Venus. This river doesn't flood much. It moves very, very fast. But my love is high-resolution imaging. I'll be talking quite a bit about that today. High-resolution imaging is not it's not a qualitative term. It's not about how great your image is. It's using your equipment at the longest focal length that you can. And of course, the seeing will dictate that more than anything. But when I talk about high-resolution imaging, I'm talking about images at the longest focal length for that aperture. So it varies, depending on the aperture you're using.
How do you estimate seeing visually?
Well, there's some really nice tools for estimating seeing, and of course there's the Pickering image of the star. It's funny, once you get into planetary imaging, you're working with a quantitative product, which is a number of frames. Say I capture 3,000 frames and I can use 20%. So while I'd say, I usually use the Pickering scale of 1 to 10 if I were going to talk about seeing, but a more meaningful discussion of it for me is how many frames out of 1,000 can I use. If it's phenomenal seeing up my way, I can use 300 frames from that 1,000. You'll see a pretty nice solar image, sunspot image that I took earlier this week, where I used 200 frames out of 6,000. So it's kind of an interesting question. I mean, seeing, describing the airy disk of a star is very good for visual observing. It's not so meaningful for planetary imaging, because what we're doing is pulling frames, from that video thing, which you'll see in more detail in a little while. But you can do things by doing that sort of defy the seeing. And the seeing is not just about how the airy disk looks, but what does the deformation look like? Can I align images of Jupiter? Is the deformation, go from a football shape this way to a football shape that way? Or is it a circle that is always a circle, but sometimes it's sharp and sometimes it's not? So they will have vastly different results in how good an image I can make. I haven't done a whole lot of lunar imaging in the last couple of years, mainly because it takes a tremendous amount of time to make these images. But I do love them, and I kind of developed a reputation at one point for doing lunar imaging and processing it in a natural way. A lot of what I do is work on the processing values. Yeah?
What elevation are you taking from it? Do you get much atmospheric distortion?
Well, I'm about 400 feet above sea level in Buffalo, I think. So, no elevation, and I have, terrible seeing 95% of the time.
Yeah.
Very much like what you have.
I couldn't get the power button to go on. I didn't know where it was.
I'm sorry, go ahead.
I couldn't see it, but I had to ask him.
Well, a lot of it is weighting, and a lot of it is how I process the images, which I'll show you. I think it'll make more sense once we get into that part. This is kind of a fun big mosaic, which is called Kleine Nachtmusik, which is called that because if you know Chuck Wood's Lunar 100, the 100th object is the Ina caldera. It's a very difficult object that's 30 meters deep, and it's only illuminated where you can see it visually, very small amount of the month. It's actually captured in this image. It's the only image I've taken that has Ina in it. So one of the things I love to do is name my images. And one of the things I'll talk about is if you have interest in publishing images, a good name goes a long way to selling it. So this is a fun one to compare. This is the 2.5 meter Nordic optical telescope, early 1990s. A state-of-the-art image at the time. And this image is 15 years later from a backyard in Buffalo with a 1/4 meter telescope. So 1/10 the aperture in diameter, a little more resolution. And this is purely the image processing techniques. Yeah?
Due to better optics? Or?
it's due to different processing techniques. This kind of processing that some people call lucky imaging, but being able to work with a video and look at the individual frames and choose only the sharp
I
ones
could do this.
is what allows us to do stuff like this today.
So how many frames was that in total to get that Saturn?
Not very many. I mean, usually Saturn rotates really quickly,
That's what I was
and so it's just like with
That's
Jupiter.
really
I usually, I mean, you've got to get 300-400 frames. There's not that much advantage between 1,000 frames and 300 frames.
Right.
There's a tremendous advantage between 300 and 3.
Right.
But it's a mathematical expression of the advantage of using multiple frames. This was 2004. It was taken in Florida with a TU cam. All the other images were taken with a DMK camera from my backyard. And of course, the last one is fabricated from the one right before it, because if you remember in September of 2009, when the rings went edge on, Saturn was about,
In the
I
sun.
can't remember, about 10 degrees away from the sun.
Yeah.
So nobody saw it. The Hubble Space Telescope wasn't able to point toward it. So I created that by rotating that last image. And this is a little animation made from the same images, which is
Oh, that's nice.
a fun teaching tool. Yeah, I enjoy this. This actually was just published by Phil Plait on Bad Astronomy. He had seen it for the first time. It had quite a play in Astronomy Picture of the Day and stuff when I first did it. But Saturn is, again, just about ready to disappear behind the sun, so it was a nice time to look at this again.
What was the aperture of the telescope that you used here?
10-inch. My
10
biggest scope is a 10-inch.
Okay.
So that's what I use for all the planetary and lunar imaging, and some of the high-resolution sunspot images you'll see shortly. So the big thing that comes up is like you can do, yes?
What kind of camera do you use?
You'll see them in a little bit. I have 4 cameras, and there are pictures of all of them in a little way. So pictures of the telescopes, too. So, we can get great results from our backyards in Buffalo or in Vestal, but Cassini is there, so it's quite frustrating sometimes. I don't know if any of you are Cassini groupies, but the Cassini images are the most breathtaking images I think I've seen anywhere. They're just incredible. I'm lucky to get some previews of some of these images from the science leader of that team. And this was an image taken at the Winter Star Party. I mean, I'm able to get some pretty nice results with my little tiny, little big man telescope. But now again, we've got a machine out there, 2 of them, orbiting the sun, taking pictures, 24 hours a day, 365 days of the year. Although you might notice, if you look closely, there's a hair. So, what the hell is that doing? But the question is, why do we keep doing these things? And then most of this talk is going to be about why I do what I do. Yes?
How far is that flare?
I don't have a measurement on it, but it's tremendous. I mean, you can tell by the curvature of the sun that it must be 300,000 miles or something like that. This is, one of the great, the top 10 of the SDO in its first year. So one of the things we can do in image processing is we can attempt to create something that is amazing, which is what your eyes can see. Your eyes, if you do visual observing and then try and take pictures and compare the two, your eye has this beautiful ability to adapt. It can adapt to many different levels of brightness. It has tremendous dynamic brain, not dynamic brain, I was going to say your brain has tremendous dynamic range. And the same thing is true with field curvature. You go take a picture with a refractor, and all of a sudden you got field curvature. When you look at it visually, you don't see any field curvature because your eye can adapt for the focus differential between the edge of the field and the center. So by doing stuff in Photoshop and working, this is a lovely image taken by Stefan Seid, who's a friend of mine from Germany, who's a wonderful astrophotographer. And I did this image. It was one of the first images I had published, but it's a double exposure, attempting to create the sun, the moon, and the crescent as it actually looks to the eye, which is both parts are exposed properly. So a lot of what I do is attempting to work with my processing values to create that visual experience and be accurate to the visual experience which has led me on a couple of interesting paths, I think, in processing images of the sun, which is a very complex object with a tremendous dynamic range, and there's no right way to show it. Just a quick run through of a few images taken from my backyard. This was last year when the southern equatorial belt of Saturn was gone. I don't know where it went, but it came back. This one's missing the more recent image. It comes up later on in this slideshow. Mars, of course, is coming up again for an apparition this year and next year. And then one of the things that we can do that's very difficult for professional observatories to do is we can image at the drop of a hat. So when there's a dust storm, try and get the Hubble Space Telescope to point toward Mars on a day's notice. This was 2 days in October of 2005, and it shows this marvelous dust storm that was visible in North America and changed quite a bit. One of the things I love is in the first day the dust lined the Valles Marineris, which is a huge feature on Mars, but it's invisible from Earth. You can't see it visually. It's just there's no contrast there to see it. You can only see the albedo markings, but not craters and valleys. Yeah.
Is that from your 10-inch telescope too?
Yes, this is all 10-inch stuff. But when the dust lodges in the valley, you can see it. The largest valley in the solar system, largest canyon. And an interesting thing to try and capture is the beauty and mystery of Venus and its cloud belts. This was taken with the Botter CAK filter, which is a fairly expensive near UV filter, which does a nice job on clouds of Venus. And this is an interesting picture, which I'll tell you more about as we go on. It was an image that captured a lot of imagination across the internet, and it's really just a processing decision of how to do this. Both the color that's utilized and the technique of inverting the solar surface so that there's limb brightening instead of limb darkening. Everybody knows the sun has limb darkening, but the prominences, if you want to see them, have to be brighter than the disk. And in order to do that, if you make a dark edge of the sun, it looks weird. It just doesn't look like anything that you really see. So this is a processing technique that I'll be speaking more about in a little bit. You can watch sunspot mitosis, which is always a lot of fun. Sunspots change over time. This one split apart, and as it rotated around the edge, it became two separate sunspots. So here's what it looks like to look through my 10-inch Mac. You'll see more about it in a little bit. It's a pretty rare telescope. Roland Christen in Astrophysics made 30 of them. I have one of them. This is in a reasonably good night of seeing. And another thing that you can see, let's see if I can do this without skipping to the next slide.
Is a wobble from atmospheric disturbance?
Yes, you're seeing atmospheric distortion there. Saturn is nice and steady. If you look at the individual frames in this, you can see how noisy they are. There's not really much to see there, but when you move it, you get a sense of what your eye does when you look through the telescope. I mean, you can take the good bits of that. Your brain is pretty good at getting rid of the bad stuff and accepting only the good information, so you can begin to see the Cassini division. Even though it's only visible in a handful of frames in this, there's enough of it there that if you watch that area, you can see it. A couple of other things. Saturn is very dim to the 10-inch. It's quite a difficult subject because there's not a lot of light. Mars, better. This is a night of not particularly good seeing. And this is a fun one because here there's all the light in the world, so it's nicely exposed. But I mean, when you look at the moon through your telescope, it often looks like that, right? And it really gives you a sense. This is a fun one to do the stop frames because some of these frames are quite beautiful. Whoa, stop. Sorry.
He doesn't do deep sky, does he?
Some of these frames are just awful, and then in some of them they're actually quite good. And then the whole practice of what I do is looking through this information frame at a time and pulling only the sharp ones to develop into the final image.
How many frames per second are we looking at?
That should be 30 frames a second, I would say. I have a newer camera now that'll take more.
Are you shooting at prime focus?
No,
No.
with those planetary image, mostly with a 2x Barlow.
2x.
So most of my planetary stuff at 7.5 meter focal length, occasionally 11.5 with the 3x Barlow. So this is the surface of the sun in the daytime through the 10-inch Mac. You can begin to see granulation in some of those frames. So it's, you know, if you get some fleeting glimpses of it. This was a very tiny sunspot. You can tell by the size of the granules. And this is the processed image of that, with a beige color interpretation in the black and white data. Remember, I'm only using black and white data, so all of the color is either applied with filters or applied with colorization in the case of the sun.
Do you do that just to get better resolution of the raw image that's coming out by shooting in black and white?
Yes, correct. The black and white cameras have better resolution than the color cameras.
I mean, on your webcam, do you just turn off the color and shoot?
No, it's a black and white camera.
Oh, it's a black and white
There's
camera.
no color, no Bayer filter over the chip. It's a
okay.
monochrome camera. This was this week. Have any of you been able to observe this sunspot group this week? Oh, it's too bad.
the internet.
It's really gorgeous. It's one of the biggest sunspots of this solar cycle.
1320?
This is 1302.
Oh, two, I'm sorry.
1302. It's really wonderful. Again, Phil Plait on Bad Astronomy published this image, and he has an image of the Earth put in here. The Earth is about that size. Really gorgeous, dramatic sunspot.
You know, the rice grain effect is, what angular resolution is that to see the rice grain? Is that?
You know, I had somebody mention that it was sub-arc second resolution.
Like-
I'm really not sure. I haven't measured it. The granules are about 1,000 miles across. I believe they're said to be about the size of Texas.
Oh,
And I love that. I try and imagine what it would be like to live in a world with that many Texases. They're terrifying. It's one of those things you have to edit out.
It'd be better seeing them.
But it's true. It would be nice. And no rain. So, but this is an example of a single exposure, single frame. So you get a sense of what has to be done to have all of the dynamic range of the sun in one image. Another one showing a higher magnification through a big prominence off the edge. And another view. Now this is through my scope called Little Big Man, which you'll see in a minute, which is using a 90 millimeter Coronado filter, much like Barlow Boboscope, I think. Also a 90 millimeter filter, right? And this is the resolution that I was able to get by working with only the sharp frames from that data. So I do a lot of taking pictures of prominences. I really love these things. They're different every day. Even during the time when there was no solar activity in terms of active regions, there are always prominences. And if you like looking at clouds and seeing shape, anybody remember the word for seeing shapes in clouds? It's a crazy word, I just had a blog post about it, and I haven't memorized it. But you can do the same thing with solar prominences. They always look like stuff. I think I have a closer look at some of these here. Moves a little bit. Pick out a couple of my favorites here. Unicorn one is one of them. Gazelle.
Oh, yeah.
These are some earlier ones. There are a few that just really look like what they are. That one at the upper left, the one next to the Clash of Titans, always looks like the Iwo Jima Memorial seen across from with the horizon blocking most of it. Yeah. This is a funny one. Anybody know what this looks like?
It's a sailboat.
It's a very famous picture. That's a dead
Yeah.
ringer for this. I'll show you what it is.
Oh.
And with Sasquatch walking off, the only known picture of Sasquatch. He appeared on the sun. Just a few. These are mostly older images. The newer ones that I've taken, in some ways, a lot better. But there were some very big ones during the last solar active cycle. So I just run through a few of them.
Is that thing to record on?
This is a really great thing that you can do without having a
90
double-stacked solar telescope.
Like that.
In some ways, the wider bandwidth is better for viewing prominences. So I have a very simple telescope with one filter. It's not double-stacked, and it does a great job in the prominences. This is probably the most dramatic solar prominence I've ever seen. It just had a kind of character that I haven't seen in this solar cycle yet. It's like a bonsai tree. I call it the bonsai prominence. And one of my favorite things about it, it was one of the 99 images selected to travel in this show from the Earth to the Universe, which was mounted for the International Year of Astronomy. It's mostly NASA images, but there are some amateur images in it too. Greg People has an image in this show as well. And it went all over the place, so all sorts of countries that we don't get along well with diplomatically, but we get along fine with in the world of astronomy. So it's kind of a neat thing. So here's where I do my work. This is my temple of astronomy. That's the sun rising on the first day of spring on my street in Buffalo. You can tell it's not the first day of fall, because the first day of fall is beautiful, and the first day of spring looks like every other day in winter, except there's no sun. There's nothing green showing anywhere. But the great thing is that the sun on the first day of spring reflects in the storefronts on Elmwood Avenue, and it's very much like a Mayan temple. You only see this on that day. Here's a picture of me with Big Boy, which is my AP 10-inch Mac CAS. It's a wonderful instrument, tiny central obstruction, so it gives a spectacular view of the planets visually. It, people call it refractor-like. It's really optimized for planetary work, and a very long focal length. It's at 14.6, so not a great deep sky imaging telescope. And this is my other major imaging platform called Little Big Man, which is the world's smallest 90-millimeter solar telescope. I can say that confidently because this is a 92-millimeter f4.8 refractor. I don't think there's a faster three-element apochromat in the world. You'll see a picture of it once it's all closed up here. I have one more picture. I have a few too many scopes to make most people, including my wife, comfortable. This is an AP 6-inch 155 from a number of years back, when you didn't have to wait in line for a decade to get them, and contrasted with the stowaway on piggyback on it. So here's my collection of astrophysics telescopes. You get a sense of the difference in size. It's a great lesson in the difference between a 3.5-inch telescope and a 10-inch telescope in terms of how big.
What was your wait time on the Mac CAS?
There was no wait time. I signed up for it. I don't know when I signed up for it. I mean, they only made 30 of them. So when the word came out that was being made, I guess a lot of people signed up. I had a very funny experience with that, actually. I had just gotten the 6-inch, which I waited about 5 years, I think, to get, maybe, from when I signed up. With this waiting list, I don't know if any of you are on the AP waiting list, and you don't really take it seriously. You put your name on it. If you get called, then you got to decide whether or not to buy it. But there's no deposit. It's kind of like, I'd love to have one of those, so you sign up for it. So I had gotten the 6-inch, and I was so excited, and my bank account was suffering from the balance due. And I had, a week later, I had a call from Marge Kristen. And I thought, well, that's really nice. Marge is calling to see how I like the 6-inch. And I figured, but that's kind of odd because I have 3 other telescopes. She never called to see how I liked any of those. And she was calling to offer me the Mac cast, which she called everyone because she wanted to ensure, one, that it wasn't going to be turned around and resold. And I said, Marge, I just sent you whatever the hell the balance was on that telescope. It was a lot of money. How am I going to come up with that scope was $10,900, and I had to pay the whole thing because it was ready. She called you when it was ready to ship, and I said, Marge, I got to think about this, and she said, okay, I understand, and I called her back 15 minutes later. And I said, what am I going to do? I mean, I can't turn it down. So I sold one of my children. So here's a few pictures of astrophysics. Last year, when was this? This was the last Midwest Astro Imaging Conference, which if you know Al DeGudas, who edits, what is that thing he edits? Astrophoto Today, Astrophoto Insight. He's a wonderful guy, and the Midwest Astro Imaging Conference was the best of all of them. But it was never that well attended, so Al didn't do it this past year. But it's a great event. If he does it again, if you enjoy the trip to Chicago, I'd really recommend going. They're one of the few to do a planetary presentation. I don't know if you've noticed, but the Advanced Imaging Conference in California never has a solar system imager included for some reason. But anyway, I met at this conference Dave Jurasevich, who's a great imager, and the superintendent of Mount Wilson. And Marge and Roland invited Dave and I to come after the event up to Astrophysics. And they met us there on a Sunday. And we had lunch with them. I got to ride in Roland's 2005 souped-up Mustang and let him show off how fast he can drive it, which was a great experience. And but the best thing was getting a little bit of a tour of astrophysics. Here Roland is showing his technique for recalling the focus using a piece of blue painter's tape. Roland was showing us the gear. They were doing a run of 900 mounts. Somebody was talking about who puts the teeth in these gears, and Roland made that big smile. And here Roland is in the optical shop showing us the possibilities of glass that he's able to get. The far one has been rough cut or deformed. I'm not even sure if it's cut, if it's ground, or it's deformed as a casting. He doesn't buy those. And this is a ribbon blank of optical glass, which he doesn't buy either. He gets these rough cut slabs of glass in the middle. But a beautiful thing to look at. I mean, look how transparent that glass is. There's not a bit of green to it anywhere. That's optical glass, costs a fortune. That piece of glass is probably 2.5 inches thick. One of the polishing stations.
So does anybody but Roland push glass?
No. Roland is the only person working in the optical shop. He has had apprentices in the past. At this point, he's the only one working in there. He's showing us here, I think I have a photo of it. Well, maybe not in this short presentation, but he's, let me just go back here. Right behind Roland there is his Opticam grinding machine, which uses these diamond grinders, and it can rough in a blank in something like 8 minutes, I think. It's pretty impressive. So his spherical shape is ground, and then Roland spends his time doing the final aspherizing and final polishing in these things. He can basically turn out an optic a day. And here he's showing the technique, working with the interferometer, of doing a final polish, a final correction on one of the, I believe these are 130 millimeter objectives. So he'll make these markings of what has to be lowered and what has to be raised, and he'll do the final polishing. I think there's a photo of it here. He uses his finger with grit at the very end to take off microscopic levels of glass. It's a beautiful shop, clean as a whistle. Just if any of you have bought any, have all of you bought something from Astrophysics? It's really something to, buy a diagonal, buy a 2-inch adapter, you'll be so impressed with the company and the quality of customer service, the attention to detail in everything they make, and everything is a good deal. I mean, people get aggravated because of the waiting list for the optics, but you can buy a Max Bright diagonal off the shelf, and it's just a spectacular piece of machining. Here's a collection of 130 objectives. That's a pretty-
Where does the interferometer come from that he uses to check the figure with? Is that something commercial, or did he build it?
No, I believe it's made. I know that the reference blank that he uses was made by, Peter Saravallo.
Oh, so he has to have an optically flat thing, and he
Oh, yeah.
and he
Right,
reflects light off of both of them somehow.
right. I don't really know the process that much.
Mhm.
That's in a much messier room. I don't think I had a picture of it there. I have a whole talk on my visit to astrophysics. The photos are not so great because I was torn between wanting to listen and pay attention and take photos. But I have some pictures of the castings. They're not castings, I'm sorry, the machining of the motor housings and the mounts and stuff. I mean, if you're into machining, it's just really beautiful, beautiful stuff. So this is my daughter Sophie a few years back, showing the size of the stowaway refractor closed. Sophie hates these pictures, but she wants to keep them in. And these are my two imaging source cameras. I now have 4 cameras, and I don't use the imaging source much any longer. These are 8-bit cameras. They're capable of 256 levels of gray. I'm now using point gray research cameras, which are 12-bit, so they do thousands of grays, which is helpful for some subjects. They're also smaller, as you'll see. Here's a picture of the Flea 3. I just got this recently. Tiniest thing you could imagine. It's just
What's the cost between this and the DMKs are fairly inexpensive?
yeah. The DMK's what about it's
$400
$300?
or $500.
Yeah, it's similar. It's not. It's more, but it's not that much more. This uses FireWire 800. I believe the DMK still use FireWire 400. So, and this will do 120 frames a second at 640 by 480. So it's very fast. And that sunspot image I showed you earlier is a mosaic of 2 frames from this camera, capturing at that rate of speed, which really helps when you have microseconds of good seeing. This is sort of a fun image, these 2 images showing you what we do by changing filters. This is a near-infrared filter, taking a picture of my daughters. And this is in blue light. So these are some of the filters in my planetary camera. You know, we're used to what a blue image of Saturn looks like and what a blue image of Jupiter versus IR in Jupiter. But this is what it looks like in teenage girls. Can you guess which one of these they like better? This was taken about the time that Twilight came out. Definitely their favorite over the blue light complexion. Although I kind of love this one. So I'm going to talk a little bit about the process of making some solar images now. This is data on what is a normal day of seeing in my backyard. But the amazing thing about solar images that anybody who does solar observing can tell you, the seeing changes momentarily. You'll have terrible seeing, and then the seeing is good. It never happens with planetary stuff. If the seeing is lousy, it might get to halfway lousy, but it never gets good on the same night. But this was, what's the time here, 1:42 p.m.?
Mm-hmm.
Here's another video from 1:54. Quite a bit of difference. I mean, there's no sense taking pictures from the other scene, but this is good enough to make a decent image. This is showing you the capture program that I use on my Mac. I only use Macs, so chances are none of you are using the software I use, so I don't spend a lot of time talking about the software. This is a program called AstroIIDC, which controls the camera using the FireWire bus. Shows you the simple commands or tools I have. I can adjust the gamma, which is the contrast, the brightness, which is the gain, and of course the exposure settings. And it captures all these nice logs, so if I want to remember back at what the experience was, I can look back on it. This is another screen showing some of the settings I can use. It's a very nice program. If you have a Mac, I think it costs about $100, but it's definitely worth the money. So what I do after I capture this data and I process it, I'm looking through the data to find the sharp frames. There's two ways to do it. I can let the software do it, or I can do it manually. Doing it manually is a royal pain, but I do it on very special occasions when the data is just spectacular, or I'm really, trying to slice hairs, in the quality of the image. But Astro IIDC does a pretty good job of creating a histogram, estimating the quality of the frames. So it's judging sharpness, basically. And there are some tools I can use to make sure that it doesn't mistake a very noisy frame for a sharp frame, which is what it wants to do. And this is showing you the red frame. The red part of the histogram is what I'm going to select. So then, after I've got my selection, I can scan through the individual frames. So what I do is I err on the side of too many frames, and then I look and see what the software selected, and I see if I agree. If I didn't agree at all, then I'll do a different type of selection with some other parameters changed. But generally, it does a pretty good job. And what I do is I go down to the last ones, because they're sorted by quality, with the first one being the best, the last one being the worst. And I'll go look at the last ones, and I'll decide I can exclude them if I want to. And if they're really distorting the image, I'll get rid of those. So then I've got 109 good frames. In order to process them, I need to align them. And Astro IIDC lets me align them more than once. Because if you can imagine, when you got distortion, it's not just that the image is fuzzy, the image is changing shape. And if I align the entire, whatever it is, whether it's a planet, the sun, if I align it on one spot, I'm going to get a nice sharp area in that spot. The further away you get from that, it's going to get furrier and furrier. So Astro IIDC lets me choose different regions. And for some of these things, I might choose 10, I might choose 20, and it will actually make a mosaic afterwards of these regions, which sometimes I use and sometimes I don't, depending on how good a job it did. But this is called multiple area alignment. So here's a rough stack here with a little bit of sharpness. These changes are subtle. And the tool that we use for sharpening is unsharp mask. You can do this in wavelets and registacks. It's all the same thing. And I'll show you what unsharp mask. Anybody remember doing unsharp mask in the darkroom? I'll show you how that's done. It's actually a very interesting technique. You know what the main tool is in unsharp masking? It's Gaussian blur. Think about that a little bit. It's really, really bizarre. This is just a few slides showing my feeling about unsharp mask, and I'll go into more detail on this. This is the difference between no unsharp mask, a radius, which is basically a zero radius. This is a radius of less than 1 pixel. And here's a radius of 3 pixels. So ugly, not ugly. And I'll explain why I think our mind wants us to do the ugly version in the center as opposed to. If there's anything that I do that may be a little different than what other people do or a lot of other people do, is I'm very delicate with the unsharp mask. I think that you create edges where there are no edges by using unsharp mask, or that is the tendency. This is the one slide that has words on it. It's really true. This is really true, and I'll explain why that happens. These are mock bands. These are, of course, just different gradations of gray, right? And they should look like just flat things of gray, but they don't really. Just a little bit more. I mean, that's what we're seeing, or what's there, and this is what we're seeing, right? You see the illusion when you look at that thing? Your eye increases the brightness on one side and decreases the brightness on the other to intensify that edge. Our brains love edges. But there's a lot of stuff out there, and those of you who do do deep sky stuff, you know that creating edges in nebula is very controversial. I just blurred this a little bit and then applied an unsharp mask. I mean, that's a very easy representation to do of that original data. It really is not true. So we've got to be very careful with what we do when we use unsharp masks.
Is unsharp grouping pixels together?
This is what unsharp mask is. I'm going to take you through it. It's a tool in Photoshop. Everybody uses it. And sometimes it's called sharpening, but the name of the tool is unsharp mask. What you do is you blur the image and you subtract the blurred image from the original image. It's hard to see it in negative, which is what it is, but this shows you a little better. That's the only change that's happening from this unsharp mask. These edges are then applied back to the original image. And you get, well, this is still the original image. It hasn't changed. Here's the change. And this is a great example, I think, that different subjects can take different amounts of unsharp mask. 18-year-old girls can take unsharp mask much better than 57-year-old guys. But it's the case also with Saturn, because the disk of Saturn is very low contrast. You can sharpen the heck out of that, and it won't look unreal. I mean, it will look unreal if you ever look at some Saturn imagers, and they got these really sharp, defined bands that you never see through the eyepiece. But in general, it looks pretty good. But the rings will look terrible. If you sharpen the rings with the same amount of sharpening, the Cassini division will go from 4,700 kilometers wide to about 7,200 kilometers wide. It gets really big.
Another question I have on this. When you use unsharp, are you bringing out information from an information theory point of view that's buried in there and bringing it out, or are you faking it by making things look sharp but you're adding information in a sense to the image?
Well, it's a very interesting question. I don't think it has an easy answer. I mean, unsharp masking will add contrast to detail. So in doing that, you can, like I have every one of those images of Saturn in that 6 years has a reference to the Yankee division. I mean, can the Yankee division be resolved from Earth? I don't know. I mean, it's in the right place, but there is a contrast difference in the data. And by unsharp masking it, we can unveil it. The Yankee division is, if I'm remembering correctly, about 320 kilometers wide. So if you do the math on that, I can't remember stuff anymore, so I apologize. I can't give you the actual data. But my memory is it's about the size of a red blood cell on my chip.
So the information is really there, because I use it too. I use it with a 3.5-inch telescope, and I see stuff in the final image that I never dreamed was when looking through the telescope, and it's there, and it corresponds to real stuff, like you said.
It is there. I mean, there are some people who use unsharp mask and make images of satellites, that I don't think is sometimes it's not real. I mean, sometimes it's diffraction effects and other things that are, so you have to be careful with it. But there's also an issue with naturalism. I mean, you can create edges. I don't know if those edges are really there. I mean, it's one thing with Encke division, but then there's another thing with what are the bands of... I mean, now we know what Jupiter looks like. I mean, we've had spacecraft that are there. So it has to be used with restraint. I don't think it really makes up data, and I don't think it's really that important, the data that we are presenting, because we have spaceships there. Yeah. Unless we're saying that there was a satellite hit or a comet hit on Jupiter and it never really happened. That can get controversial.
Hey, one last question on this. A thing that I noticed, I'm not that up on this stuff, but when I use unsharp, there's another parameter that goes along with it, and it's called the strength. Are you going to get into that?
Restraint?
Yes, strength.
Oh, strength. The strength is
There's like a trade-off.
I never
between the
touch. I never touch the strength. The only thing that I use is the top slider. Is the top slider?
The top slider is unsharpened, and then there's strength. This is K3 CCD tools.
Oh, okay. There are three parameters in unsharp mask, and I can't remember the names of them. The middle one is the pixel radius, which
Yeah.
will control
Oh, maybe so.
the level of contrast, the level of features that you're adding contrast
Yeah, maybe it's the
to.
radius. That's what I'm thinking of.
The radius
Yeah.
is very important.
Yes.
The other thing is just a strength factor, which is
Yeah.
important, but the place really to experiment is in the pixel radius. Because you can use a bigger pixel radius if your features are very big, which they are on Jupiter.
Yeah.
Cloud band detail in Jupiter is mostly pretty large size stuff, especially the bands on Saturn.
So when you're talking about radius, you are actually conglomerating pixels together, probably, and making four
Yes.
pixels into one.
Well, you're treating pixels as if they are. That's right, as if they are one, which becomes very dangerous if you have fine detail. And I think that processing on this prominence showed it. I mean, you can take it to looking, really contrasty, but just unreal. I mean, you see enough badly processed planetary images that you know when something's bad.
Wasn't David Mallon the first to use unsharp masking with Astro Deep Sky?
I don't know. He certainly was a pioneer. You may very well be right.
I think it was not on digital, but on film.
On film? Yeah, it was a film technique. That was a darkroom technique that I just showed
I think
you.
it was the first to actually do it.
Yeah, well, just one point, at least in deep sky stuff, when you pick the parameters, you can pick the parameters to actually zero in on the noise. So instead of enhancing the signal, you're enhancing the noise. And a lot of times that's where you're getting this Dougly stuff from, is you've picked the parameter that's you're throwing away signal and bringing out noise.
Well, that is definitely a possibility. And one of the goals of this type of work is, and deep sky stuff, is to eliminate the noise with exposure. Here where we've got noise in the original frames, but that's the advantage of stacking hundreds of frames, is you increase the signal and decrease the noise. But you're absolutely right. If there's a lot of noise in the image, you can do that. Sometimes you can apply a Gaussian blur to an image before sharpening, and that will subdue the noise before the sharpening is brought in. So here's a couple of other imaging techniques. One of the things I often do if I'm just going to process a prominence is create a large circle. And I do two things with this. The first one is kind of obvious. Remember this number here, 3,290. We're going to come back to it later. I mean, one of the nicest things to do is to create an occulting disk in front of the disk. You can see pretty easily, right, how much easier it is to see faint stuff in the prominences if you don't have the sun in your face. And that's the reason that technique is used. In the same way that we like to not have lighting in our face in city lighting ordinances, because it doesn't, aside from destroying the night sky, it doesn't help you see anything any better. It just blinds you. This is an example of an old image where I just used the magic wand to create that, as opposed to creating a circle. It's quite a bit more attractive to not do that. I'd love to go back and reprocess that image someday. So another thing that's nice to do is just add a little bit of color, because we know that our eyes are sensitive more in the yellow-green end of the spectrum. It also helps to add a little color if you want to publish images, because nobody publishes black and white images. Astronomy Picture of the Day, spaceweather.com, and they just do not want black and white images. So another fun thing that we can do, if you remember that 3,290, is we can do a quick calculation of the size of the Earth, doing a little bit of math, knowing there's 109 Earths across the sun, and we can make an Earth-sized spot, which of course we can do with some nice Apollo image data to make it really look like the Earth, but it allows us to do some nice measuring of these things in Earth diameters at 8,000 miles. And if you wind up having enough time and don't have to go to work, you can capture multiple images of prominences and animate them, which is This one is more just kind of fun and pretty. This one is a little more interesting. As you know, prominences are almost always looping in character, right? They come in and out of magnetically charged regions on the sun. And it's really nice when they're facing you and the loop looks like this. But when the loop looks like this, front to back, it's very hard to see what's going on. And a little animation shows you that looping quality is happening front to back. That plasma is actually being thrown backwards. 3 dimensions always helps us understand things. So in recent years, I've got into different types of solar processing. I did a lot of this work originally, and then I got involved more in trying to express the sun's surface in the same image, which is almost impossible to capture with the same stream because of the huge dynamic range between the brightness of the sun. So it led me to explore some different techniques. This is just reversing the prominences. These are all old images. This is kind of what you get with limb darkening at the edge of the sun. This is an old image, but I remember being just hating the way it looked. And I just experimented with inverting the disk of the sun. And it just created this feeling that just seemed right to me. So I did quite a bit of exploration of this technique. These are some more recent images, just showing you some of the variations that are possible. This was that image we saw earlier. This was a very large prominence after a very long period of solar inactivity. Astronomy Picture of the Day published this as a kind of celebration of the new solar cycle with the end of solar minimum, hopefully. This is a single frame of data, and the two were combined to create the final image. This was 2 days later. That was a really great prominence. This was another fun title. I don't know how many of you read Dr. Seuss to your kids, but he wrote a book called The Birthday Book, which is a great book. I read it to my daughters every year on their birthday. They still let me do it. One of the things the kid got for his birthday was a pet, and he had to go and pick the tallest of allest, and that's the title of this image. And it's a great little piece of poetry about measuring these crazy Dr. Seuss characters. They had to stand back to back, and they get bigger and bigger and bigger and bigger. And you had to. It's worth a read if you have a chance. That last prominence was very tall, as you can guess.
Hey, Alan, how do you decide what color goes into them when you're shooting in black and white? Is that just
it's really just an aesthetic decision.
Uh-huh.
I mean, the sun is sort of yellow, but as you'll see, I have blue suns, which are not ultraviolet wavelengths, not in the CAK wavelength.
Could you shoot in 3 different video clips under 3 different filters and somehow combine them?
Not if you're shooting in hydrogen alpha.
Oh, that's.
I'm working with a 0.7.
Yeah.
0.7th what the heck is it? It's less than 1/10 billionth of a
Right.
meter. So all I got is red,
Mm-hmm.
and it's just monochrome. This was a very recent image of a quite nice prominence that I played with a couple of different ways. And this was a kind of a revelation. This is purely an inverted image. The values are inverted and the color is inverted. When you invert a typical yellow solar image, you come up with a blue solar image. It led me to experiment with some blue suns. This was another one that was selected from the Astronomy Picture of the Day. I don't know if any of you notice. I noticed that it's very difficult now to get an astronomy picture of the day of the sun since Solar Dynamics Observatory was put up there. I haven't had one in almost a year, and it's driving me crazy because I'll talk more about that in a minute. But they did just publish a picture of a nice prominence that came out of 1302 just the other day. It came from France, a great imager. I was really happy to see that. Pissed that it wasn't mine that I sent them also, but I was really happy to see they selected it. This was my most recent prominence image. This was just a couple of weeks ago. What I loved about this was the different character of those two different prominences. When I published them originally, I did them separately, and then I had the opportunity to make a larger image. And one on the top is called Delicato, and the other one is Fortissimo, for those of you who enjoy music. And just a little bit of a run-through of making one of these images and the parts that go into it, because it involves a lot of parts. This is about as much dynamic range as I can capture in one image. I usually brighten the prominences some so that you can see the fainter details of them. A little bit of sharpening. And then the solar disk is applied in a separate piece and added in, and then both parts of it are colorized separately. And that's the final image. In a lot of layers in Photoshop. That's how that's created. Layers are great. Okay, just a little bit of couple of side stories here to add to this talk. Anybody need to get up and stretch? Just a little talk. Doing okay? So Dave, who went with me to Astrophysics, we drove up there together and drove back, and we really enjoyed each other's company. It's a nice, about an hour and a half drive from Chicago up to Rockford, where Astrophysics is. And several months later, he gave me a call and asked if it was like the call Marge gave me about the 10-inch Mac. He said, "You think you could find time to come out to Mount Wilson and use the 60-inch to take some pictures of Jupiter?" And I was really booked. I had a lot of stuff I had to do. I had to take Sophie back to school in Chicago. So I said, "Dave, let me think about it." And I called him back 15 minutes later, because he could only. I thought maybe we could figure out a day, but he had the Advanced Imaging Conference and some other stuff going on. He had a 3-day window that he could do. And I dropped my daughter off at school. I took all of her stuff out of the car, put it on the sidewalk, and I got back in the car, drove to O'Hare, and she hasn't quite forgiven me yet. This is a picture of the rising moon on the way to California. That's Dave. Dave has his own dome on Mount Wilson. Mount Wilson is an amazing place. It's absolutely beautiful. It's famous for its seeing. It was chosen because of its unique location. It gets a laminar flow of air and has some of the best seeing in Southern California. You know, it's only 18 miles from downtown Los Angeles.
Did this observatory survive the fires there?
Everything survived the fires.
It did, okay.
Yeah, the fires came within a quarter of a mile of Mount Wilson. Again, I have a very long talk on my visit to Mount Wilson, which was one of the most magical astronomical experiences I had. It was pretty much me and Dave and a couple of other people up there by ourselves for 3 days. This is Dave's bubble. This is not. I'm sorry, this is wrong. I made this mistake in Neef, and I had 600 people come up after me and complain. This is the Bubble Nebula. But Dave discovered a nebula very close to the Crescent Nebula, which is called now the Soap Bubble Nebula, and has his name after 4 years, I think, finally. He captured that on Mount Wilson. But this is an astronomy picture of the day of Dave's interpretation of the Bubble Nebula. This is a view from the solar telescope, the 150-foot solar tower of the 100-inch Hooker telescope on Mount Wilson. Just a little panorama of what you see from the gates of Mount Wilson. So I went out there, Dave met me, got in about 3 o'clock, and it was a 3-hour drive to get up there because the roads, because of the fire, had been, many of them were closed. There's downtown Los Angeles poking out of the marine layer. That's not smog, that's marine layer, which is all over that place, except Mount Wilson. It's really, scenically, it's spectacular. In the long slideshow I do on this place, the sad story of it is the building of Mount Palomar, which is not nearly as pretty a place. But, you know, all of the people who hung out on Mount Wilson, you know, from Einstein and Shapley and Hubble and all of these, you know, famous luminaries, you know, Hubble kind of abandoned Mount Wilson, went off to this beautiful new telescope on Mount Palomar. I don't think I have the pictures here. I'll just run through these quickly. So this is the 60-inch, prepared for our night's work. But the telescopes on Mount Wilson are like erector set pieces. They look like 19th century construction. Welding had just been invented, but they didn't trust it. They riveted everything together on Mount Wilson. Mount Palomar's telescope, which you know is a beautiful Art Deco design, it's only 30 years older than this, but so much had changed. This is a picture of the 60-inch. If you look down on the top, that's a 20-foot ladder. If you look on the top step of the ladder, you can see my laptop. And if you look really closely in the focuser, the 4-inch focuser, that's my Scorpion camera, 1600 by 1200 pixel webcam. I have a focal reducer attached to it because the focal length of this thing is 24 meters. So it makes a really big Jupiter. With a focal reducer, I was just able to get it to fit on the chip. And there it is pointed up at the sky. And there it is pointed at Jupiter. One of the fun things about this, you know, I mean, Dave says you always get people up there because they do public observing in this. You can rent this if you've got a bunch of friends and $1,800. You can rent this thing for a night. Yeah, I think you can do a half night for $900, and it's a great, amazing thing to do. I got to use it visually a little bit, but you get up there, and you know, to look through it, you sort of lean against it, and you think, like, I can't touch the telescope, right? I mean, you could have 12 people hanging on this thing. The mount is so, it's just unlike any telescope you can imagine. This is the 100-inch hooker.
Are they doing any science?
Previous was what happened.
Yes, with the hooker they are.
What average was the previous?
There was not a project on it currently when I was there. And there's quite a bit of science on the mountain. The Chandra array is an interferometric array of 1-meter telescopes, and they have some of the highest angular resolution of any telescope in the world. They're searching for orbiting planets around stars visually with that array. And this, of course, is the eureka moment of Mount Wilson when the Cepheid variable was found by Hubble, which determined that, what? That's a galaxy. This is the library on Mount Wilson. I got to sit in that chair. I had my tuchus on the same chair that Albert Einstein sat in. It was really, just the experience of being there is incredible. This is the 150-foot solar telescope. I did take an image using that telescope. It's kind of fun to see. That's Steve. He works for UCLA. Look at the computer equipment that's in this place. There's a picture of Einstein looking at the projected image of the sun from the same place with all the same equipment, just without the computer. And Albert actually went up in the bucket to look at the collecting mirror up on the top of that thing. A bucket is incredible. It's just like a bucket with a cable, and it just waves back and forth. Steve has to go up twice a day to turn the dome because the dome is not motorized. So he invited me to go up, and I didn't go. There's a picture of Steve in the bucket going up to the top. I don't do amusement park. I just couldn't do it. I really sort of wanted to, but that's where where that first picture of Mount Wilson was taken. There's a webcam up that takes picture of the dome twice a day. Another picture of that 1960s vintage equipment, and there you see the solar image projected down from the 150-foot focal length. Now I brought a setup just to try and image with that thing, to take off the lens and put my webcam at the prime focus. So there was a sunspot there, But unfortunately, it was good seeing the first time we went, and when I went back to image, the seeing was lousy. Oh, there's a picture of Einstein in the same spot. Now, I don't think, yeah, there's the sunspot. Unfortunately, this animation doesn't work too well. This is an animation made with a 1600 by 1200 pixel camera, so it's a really big pile of data. It doesn't move very smoothly. But the most interesting thing about this, the sunspot, there was no working with this data. The data was terrible. But look at all the stuff on there. If you think your chip looks bad, look at it at the focal ratio of whatever the heck this is, f150. It's because it's a 1 foot mirror and a 1 foot lens and a 150 foot focal length. It's like you see everything. You see microscopic stuff on it.
Don't you think they're creating something different?
So this is the image that I was able to capture from the best night at Mount Wilson, which was pretty good. It was probably the best picture ever taken of Jupiter with the 60-inch. And this was the image I took from my backyard the week after I got back with the 10-inch, which unfortunately I think is not going to get me invited back to Mount Wilson anytime soon. But it's, you know, the story, and this was a few weeks ago, with the southern equatorial belt is back in full force.
Hey, Alan.
Yeah.
A question. All these planetary ones. Now, you took these with webcams on your own telescope, right? The 10-inch Mac.
Right.
Now, the color that's in it, was that just videoed in color, or did you?
No, this is RGB imaging.
Oh, so you just get one clip out that had all the color in it.
Well, you know what? Bear with me a second here.
That's what I was. My previous question, I guess, was aimed more at planets than the sun.
Just
Oh,
to
you took 3 clips?
yep, it's 3 separate
filters.
images. If here, I'm sorry. Let me go back. I can show this to you a little bit better. I just added this.
He uses a black and
Oh,
white camera
okay,
and
yeah.
images through filters.
3 filters.
Okay. Okay, so you're combining 3 video clips then with filters.
Yeah, he's using a
Red,
much
green,
better
and blue.
camera than a webcam.
Yeah, yeah.
Yeah, this is an industrial webcam, basically.
Yeah.
And these cameras are used for parts manufacturing and stuff like that. But they're basically a webcam. They take streaming video. This was the last image with my DMK camera. I haven't yet used my new Fleet 3 on the Jupiter. But these are the 3. Well, this is what Jupiter looks like in red, green, and blue. And by assembling those images in Photoshop is how we create the full color image.
So how do you run a filter wheel in front of one of those cameras?
It's a manual filter wheel. It's
Okay.
just got a little knob on it. I turn it quickly between red, green, and blue. That's why 120 frames a second is going to be a huge advantage with this. It's a real ballet of fast movements because you've got about 2 minutes to capture all of your data in red, green, and blue before you get image shift because of the fast rotation. So the story of this is, of course, there's no place like it. Okay, a couple of other quick travelogues. How am I doing? Am I doing all right with time?
Luckily, you got the plan now.
Very good.
I think we got about 7 more minutes.
You might have, yeah, about that, okay.
Winter Star Party. Some of us have to do terrible things like go to Florida to do
It's got to
stuff.
be tough.
Yeah, it was really hard. I went by myself. I drove 3,600 miles round trip to give a talk, but I did it because I wanted to bring a couple of telescopes with me, and this was the image we got to capture there, which was exciting.
How do you get the dimensionality in there? I mean, that just looks so 3D. Is there any effect you're applying to get that? Or?
It's just the techniques that I've developed of using the inverted disc. It does add a character of
Just
dimensionality to it. Anybody notice anybody look at this? You see that little thing?
Yeah.
So while we were there, we learned that the space station, somebody said the space station is going to go over the Winter Star Party. So I looked it up, and I got this message, which was the space station is going to go near the Winter Star Party, which is a thing that you learn does not mean it's going to go over. These are really narrow events. So I did some research. I figured that if I went to Marathon Key,
I don't know.
that's the center line of the transit. I was staying on Marathon in a lovely apartment that they get for you when you're a speaker. You really want to be a speaker at the Winter Star Party. It's a great gig. It's a really nice gig. But I tried to figure out where can I go, and I did a little hunting around. There's a trailer community over here, which had a nice access road, and that's where I chose to be. And I figured I'm doing great. I thought it was 500 yards away. It turned out to be about 5,000 yards away, and it was we just caught it. It just skipped across the edge. We had, I believe, 2.5 images of the space station on the side. But it was a real exciting adventure because my talk was to end at 2:30 and this thing was going to happen at 3:20. So I had some friends get all the stuff loaded in the car. I raced out of my talk, I got in the car, drove the 25 miles. And it's, if you drive in the Keys, you can't speed. There are more cops, looking for speeders in the Keys than any place else in the world. So we got there, we got set up.
More head-on accidents, too.
And we got the image. And then I got home about a month and a half ago. My wife joined me on Lake Ontario, up about 60 miles from Buffalo, and we captured one in hydrogen alpha wavelength. So those are great things, too.
The life of Terry Liddell, right?
Yeah, Terry, he's a madman. I don't have that life. I wish I could do the travel he does. His work is amazing. Truly amazing. Actually, I think I have a picture of him a little later on.
Cool.
That is my imaging setup from my backyard with Little Big Man. So here's the last story that I'll bore you with. Here's this image that I took October 20th of last year, and I colorized it and thought, when I looked at it, there's just something about it that I really loved, and I titled it, "It's Not the Great Pumpkin, Charlie Brown." And it's, Halloween image, right? This is an easy sell to Jerry Bennell and Bob Nemiroff. I sent it to them. I was absolutely sure this would be the Halloween astronomy picture of the day. This was a great day. I had some really nice other high-resolution images captured. The scene was pretty good. I had this one. I totally knew that they would select this one, even though it looks kind of similar, and they chose this one. Which Nebula is the astronomy picture of the day. So, what are you going to do? There's like a million fantastic imagers out there. But this guy, Jason Major, is Jason Major? I got that right? Yeah, Jason Major has this really nice blog, and he follows my work, and he found the image and posted it. And he's friends with Phil Plait, who picked up the image and blogged it. And he wrote a great piece about it. I mean, it was basically, do you ever read his stuff?
Yeah.
He's a really great writer. I keep thinking there's nothing new under the sun, with SOHO and SDO and $1,000 telescopes. It would take something pretty freaking cool to surprise me. Well, surprise. And he just got into this image, and all of a sudden, everybody got into this image. It was getting picked up. It was in Wired magazine. I did an interview with NPR. What else did I do? The Huffington Post wrote a story about it. The Wired interview was really nice. AOL wrote the news story. It was in London. It was basically in every major news source, major newspaper. This is La Repubblica in Italy, the major daily in Italy, and some Russian paper that I don't know.
It wasn't Pravda.
What's that?
It probably wasn't Pravda.
No, it seemed to go more in it was a little more of the USA Today news direction. I did have someone contact me from the New York Times who scheduled 3 different interviews and blew off each one of them without calling me. It was very annoying. But basically, I gave a week of my life to following this story because it just was getting blogged and reblogged. And actually, if you Google my name and look at images, I'm actually the first Alan Friedman that comes up. But the images are 500 variations of this image reblogged, a million different places. And I just was mesmerized by it. I never had a viral experience with anything I'd ever done before. So I started following all these comments on these places. They were from love letters to any monkey with a hydrogen alpha telescope could do the same thing. You know, we able to get it. And I just was so, I couldn't put it down. I got no work done for a week. Well, the funny one was the Daily Mail, which has a lot of, just wild, you know how they do the House of Parliament thing where they boo and piss? Well, people do the same thing. And one person read, one of the interviews said that I had a 14-inch long telescope. Well, that got put into that it was a 14-inch telescope, and all these people were saying, that's not an amateur telescope, a 14-inch telescope. So, anyway, the end of it was that it was on MSNBC, and I got an interview on the Today Show, which was the first of 2 interviews I did on the Today Show about the making of this image. And if you like this stuff, you can link to it on my website. It's actually a wonderful astronomy interview. I really enjoyed it. So then Google Analytics, I was all over Google Analytics watching this. I had 250,000 people went back to look at my website, take the time to see who the guy was who made this image. So it really was a big thing. And these are the countries that visited. I have the list of all the countries and how many people came from each. Do all of you know Google Analytics?
Yeah.
Amazing tool. You can find out how many people looked at this image with a cell phone and what their cell phone carrier is. You can basically find out anything about it except who it
Their
was.
name.
that came there. Yeah. So I spent a week of my life involved in this, trying to figure out what is going on with this. Why is this so interesting? I mean, phenomenal imagers doing this all over the world. What is it about this image that was newsworthy? And I finally realized it's this DIY thing. This is what characterizes it. You all know what DIY is, right? Do it yourself. It's all about doing it yourself. And if there's a reason why I do this, and I think why you do this, it's the fact that you can do it yourself and experience yourself. And then the other side of it is the OMG factor, is you get to share this stuff with other people and blow their minds by making the images or just taking your telescope out and sharing it. And that's why I do it. Here's one of the celebrities underneath my solar observing quad. That's Thierry Legault on the left, Greg People on the right, Solar Buddies. Places you can share this stuff. The Cloudy Nights Forum is excellent. It's a great place if you're interested in solar or planetary imaging and 1,000 other things. But it's the Solar Imaging Forum here is spectacular. The Bums at Astronomy Picture of the Day, I still like them, even though they replaced me with SDO. And of course, spaceweather.com, which is a marvelous site. These are sort of my go-to sources for astronomy information. And my website, which I hope you'll visit. And now there's a link to my blog, which is on Tumblr, called Space Cowboy, or it's a Virgin Imagination. And it's the little mantra. So go out there and have fun. I think that's the end of it. All I have to share with you.
Need some whites here.
I want to thank you very much for this interesting presentation. And with that, we also have a small token of appreciation.
A T-shirt.
Yes.
No, before I was a greeting card publisher, I was a T-shirt printer.
Oh, okay. Make sure the sign says not with.
Yeah,
Okay. I want to thank
I'm
you.
only getting bigger.
Oh, thanks very much. Aren't we all?
Alan, you're still giving a presentation again tomorrow?
I will stay and do it.
And if it's sunny, what are you going to do? Are you still thinking of doing
Well, I
that?
hope you guys are not going to be the audience tomorrow, right? We're going to get some other.
Well, hopefully some of them will still be here.
Because my other presentation has a lot of this stuff in it. So hopefully we'll have some sun and you'll all be outside and somebody else will come in. But if you'd like me to, I'm more than happy to. I'm planning to stay over and talk tomorrow for the public.
Thank you
The
very
clear
much.
sky clock says 1 o'clock it's going to clear.
Tomorrow?
Good.
And it was correct last night, so it might be right.
Well, hopefully it remains correct. Okay, we're going to take a break. Dinner will be arriving, I believe, in about 25 minutes or so. And so we can take a break. our next speaker is going to have some time to set up and have dinner. Yes.
I'm going to do a quickie on Vesta Fiesta in Earth Science Lab around 10 minutes from now.
Okay,
And then
so-
we're going to have Star Trek on the screen during dinner.
Okay, very good. Thank you.
And I'll be around, if anybody has questions or want to talk more about any of this, I'm more than happy to talk.
Okay.
Tish,
Yes, sir.
give me the sign there.
Oh, that one?
Careful, Jeff.
Okay. Well, I'm sure you're all kind of weary from sitting so long, so please stand, get up, stretch.